this video we will see the design of the slab. For that the given problem is like this. A room has clear dimension 7 meter into 3 meter. The live load on the slab is 3.5 kN per meter square and a floor finishing load of 1.2 kN per meter square. Use M20 concrete and Fe415 steel. Design the slab. So as usual in our RCC, the first step is to write down the given data. So the given data are here. They have given clear room dimension, that is 7 meter into 3 meter. Room dimension 7 meter into 3 meter. And they gave live load of slab, that is 3.5 kilonewton meter square. Live load 3.5 kilonewton meter square. And they gave floor finishing, that's 1.2 kilonewton meter square. Floor finish 1.2 kilonewton meter square. And M20 concrete and Fe415. M20 concrete, that is nothing but FCK 20 Newton per mm square and Fy is 415 Newton mm square. So in design of slab, the first step is to check whether the given problem is one-way slab or two-way slab. For one-way slab, our Ly by Lx ratio, the longer span to shorter span ratio is greater than 2 for one-way slab, and for two-way slab Ly by Lx ratio is less than 2. If Ly by Lx is less than 2, then the slab is designed as two-way slab. So we will see step by step procedure. So first step is to find out whether the given problem is one-way slab or two-way slab. So for that, step 1 is to determine the type of the slab. For that, the Ly is called as the longer span. That's the longer dimension is taken as the Ly, that is longer span, that is 7 meter, and shorter span Lx 3 meter. Longer span to shorter span ratio is Ly by Lx. So Ly by Lx is, our Ly is 7 meter, Lx is 3 meters. So substitute all the value. By simplifying, we'll get Ly by Lx ratio as 2.33. So 2.33, it means what it says, our given slab is one-way slab, because our Ly by Lx ratio is greater than 2, as I said earlier. So when the ratio of Ly by Lx is greater than 2, the given slab is designed as one-way slab. So this is how we determine whether the given slab is one-way or two-way, by calculating Ly by Lx ratio by applying this. So next we'll move. Step 2 is the determination of the effective depth. So as per clause 23.2.1a, page number 37. So what it says, we'll see. We'll move on to page number 37 of IS 456-2000. So this is the page number 37 of IS 456. So clause number 23.2.1. The basics values of span to effective depth ratio for spans up to 10 meter. For cantilever 7, it's for simply supported beam it is 20, and for continuous beam it is 26. So what they have mentioned here, the Ly by L by D ratio should not be greater than 20 for simply supported slab. So now we are calculating the simply supported slab we are designing. So I am taking L by D ratio as 20. As they have mentioned, I take L by D ratio as 20. So I have rearranged it. D is equal to L divided by 20. D they gave is 3 meter. 3 meter is nothing but 3000 mm divided by 20. So after simplifying, we will get effective depth value as 150 mm. 150 mm. So next, for calculation of the overall depth, we need to assume the effective cover, that is denoted as small d dash. So next assume the effective cover as, I am assuming 20 mm. You can take around 25 mm. So I am assuming 20 mm I am taking. Now we can easily calculate the overall depth. So for that we have the formula capital D is equal to effective depth plus effective cover. Substitute all the value. D we got was 150 and we assume D dash as 20. So 150 plus 20 will be getting 170 mm as our overall depth. So this is how we calculate the overall depth. For calculation of overall depth we need to assume the effective cover. So we'll move forward. Step 3 is the determination of the effective span. So for that again we'll go for IS 456 2000 codebook as per clause 22.2a page number 34. What it says we'll see. So for simply supported beam or slab, now we are designing the slab. So the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab. So this is the one criteria. And the second is center to center of supports. So whichever is less. So this is the second one, center to center of supports. So we have to take the value which is the least value, whichever is less, by applying these two rules. The same rule we have applied for the when we are designing the beams. For slab also we have to apply same rule. So for calculation of the effective span we need to assume the bearing. So I am taking bearing or wall thickness as 230 mm. So one criteria they have said clear span plus effective depth. So clear span they gave 3 meter. They gave clear span value 3 meter and D we got was 150, that is nothing but 0.15 meter. Substitute all the value. After simplifying we will get L value as 3.15 meter. And the next criteria is clear span plus bearing. So they are not bearing value, they are not given in a problem. If they are not given we have to assume it is necessary for the calculation. So that I am assuming bearing value is 230 mm. So substitute all the value. L is 3 meter plus bearing is 0.23. So after simplifying we will get our L value as 3.23 meter. And they have clearly mentioned in clause the L value should be least of these two. Which is least? 3.15 meter is least. So I am taking L value as 3.15 meter. This is how we calculate the effective span. Next we will go for the calculation of the load. So step 4 is to determination of load. For that we need to calculate the self weight of the slab, that is nothing but dead load. For that we have the formula rho into B into D. Rho is density of the RCC, that is 25 kilonewton per meter square meter cube. Rho value is 25 kilonewton per meter cube. B value is 1 meter. So remember always when you are designing the slab, the width of the slab we should take 1 meter or 1000 mm. So I have taken B as 1 meter. D is overall depth we got was 170 mm. 170 mm is nothing but 0.17 meter. So after substituting, by simplifying we will get our dead load value as 4.25 kilonewton per meter square. The live load they have given is 3.5 kilonewton and floor finishing they have given 1.2. So in some problems they are not given floor finishing. If they are not given we need to assume. So I add it to find out the total load. So I am adding. So after adding we will get our total load value as 8.95 kilonewton per meter square. So next we have to go for the calculation of factored load, that is nothing but ultimate load. It's denoted as WU. For that we have the formula 1.5 into W, that is total load. So 1.5 into total load we got was 8.95. So after simplifying we'll get our factored load value as 13.42 kilonewton per meter. So this is how we have to calculate the load. So we'll move forward. So next step 5 is to calculation of the maximum bending moment. For that we have the formula mu is equal to WU L square divided by 8. So WU, substitute all the value. WU value we got was 13.42 and L value we got was 3.15 divided by 8. After simplifying we'll get value as 16.64 kilonewton meter, or 16.64 into 10 to the power of 6 Newton per mm in terms of mm. Next we'll go for the check for the effective depth. Step 6 is to check for the effective depth. For that we have the formula mu is equal to 0.138 FCK into BD square. So now we are calculating the D required. For that I have rearranged this formula. This formula is given on page number 96. So page number 96, here the mu limit is equal to 0.36 xu max divided by D, 1 minus 0.42 xu max divided by D into BD square by FCK. Here what you have to do is just put the xu by D value as 0.48 for 4 and 5 still. So after simplifying we will get our mu value as 0.138 FCK BD square. So I have written the simplified version of the formula here. So now substitute, after rearranging, substitute all the value. mu value we got was 16.64 into 10 to the power of 6, 0.138 into 20 into FCK value is 20, and B we have to take 1 meter. 1 meter nothing but 1000 mm. So after substituting, by simplifying we'll get D required value as it comes out 77.64 mm. So now why we need to go for the check for the effective depth means the whatever the depth we have provided, whether that is sufficient to carry this moment or not, we have to check. So our D required for this problem is 77.64. So we have provided D provided, how much we have provided? We have provided 150 mm. So our, by seeing these two, what we can conclude that our D required is less than the D provided. Therefore our design is safe. We can move further. So we have provided D as more than the D required. This is how D check is done. So next step 7 is a calculation of the area of main reinforcement, that is the AST, area of steel. For that we have the formula AST is equal to 0.5 FCK divided by F5 1 minus under root of 1 minus 4.6 into mu divided by FCK into BD square into B into D. So substitute all the value. 0.5 into our FCK is 20, Fy is 4 and 5, 1 minus under root of 1 minus 4.6 into mu value we got was 18.64 into 10 to the power of 6, FCK is 20, B is 1000, D is 150. So substitute all the value. After simplifying we will get our AST required value as 320.4 mm square. There is one more method to calculation of the AST by using the formula which is given on the page number 96. That is mu is equal to 0.87 Fy AST D into bracket 1 minus AST divided by AST FY divided by B into D into FCK. By using this formula and with the method of quadratic equation, we can also calculate the AST. So, or by simply remembering this formula, we can calculate the AST. Both the answer will be same. So next, now we have to assume the diameter for calculation of the area. So I am assuming 8 mm. Pi bars I am taking. So we can calculate the area of 1 bar. For that we have the formula small AST is equal to pi divided by d square is nothing but diameter divided by 4. So after simplifying we will get our area of 1 bar value as 50.26 mm square. Here in slab, designing of slab, we need to provide the spacing. For that we have the formula 1000 into AST divided by AST. Area of 1 bar divided by AST. So substitute all the value 1000 into AST. Area of 1 bar is 50.26 divided by AST required we got was 320.4. Substitute all the value. After simplifying we will get our spacing value is 156.86. So I am making it into 150. I am reducing this value. Why I am reducing this value means I will tell. So now we will go for the calculation of the AST provided. So for that we have the formula, same formula. By using this formula I have simply moved AST to here and spacing to here. I have rearranged the AST provided is equal to 1000 into small AST, that is area of 1 bar divided by spacing. Substitute all the value 1000 into 50.26 divided by spacing we got was 150. After simplifying we will get AST provided value as 335.06 mm square. This is the AST provided. So NC provide 8 mm pi bars at 150 mm center to center as main reinforcement. So this is how we have to calculate the AST provided. So here we need to check the safety factor for this spacing as per the codebook rule. As per clause 26.3.3 page number 46, what it says we'll see. So this is the page number 46 of clause number 26.3.3. Here B for slabs. So what they have mentioned here, the horizontal distance between parallel main reinforcement bars shall not be more than 3 times of effective depth of solid slabs or 300 mm, whichever is smaller. What they have mentioned here, for main bars our spacing should not be greater than 3 times of effective depth, that is nothing but 3D or 300 mm. We have to take the least value, whichever is smaller. So S is equal to 3 into D. 3 into D is 150. So after simplifying we got S value as 450. So they have said our spacing value should not be greater than 3D. So we got our spacing value was 150. So it is less than the 450. So NCR value is correct. So next we have to calculate the distribution reinforcement now and spacing like this. In the same way we have to we'll go for the calculation of the distribution reinforcement. So for that, as per clause 26.5.2.1 page number 48, what it says, now we have to calculate the one more thing, that is AST minimum. So what they have mentioned, minimum reinforcement, the mild steel reinforcement in either direction in slab shall not be less than 0.15% of the total cross section area. However, This value can be reduced to 0.12% when high strength deformed bars or welded wires fabric are used. So what they have mentioned here, for deformed bar we have to take the 0.12 into B into D, and for mild steel we have to take the value of AST minimum, that is 0.15% of total cross section area, that is B into D. So now we are using the deformed bar. So we have to take the 0.12% of area of total cross section area for deformed bars. So in our problem they gave our 4 and 5 steel. So for that we have to apply this. So I have written the what they have mentioned in code book, same I have written here. For 0.15% for mild steel, that is nothing but Fe250, and 0.12% for HOST bars, that is nothing but Fe4 and 5 and Fe500. So now AST minimum is equal to 0.12% of total cross section area. So AST minimum is equal to 0.12% is nothing but 0.12 divided by 100 into B into D. So substitute all the value, 0.12 divided by 100 into B value 1000, D we got overall depth value was 170. After simplifying we'll get AST minimum value as 204 mm square. So this is AST minimum, also called as distribution steels. So we got 204 mm square. This is how we have to calculate the AST minimum by applying the code book rule. Again we have to go for the calculation spacing and area for calculation of distribution steels. Again we need to assume the diameter. So I am taking the same, that is 8 mm pi bars. Here f each bar is equal to pi by 4, 8 divided by 4. After simplifying we'll get AST value as 50.26 mm square. Same, and spacing, the formula is equal to 1000 into area of 1 bar divided by AST minimum, which we have calculated just now. 1000 into 50.26 divided by 204, we got AST minimum value. So after simplifying spacing value we got 246.37. So provide 8 mm pi bars at 200 mm center to center as distribution steel. So I am spacing value, I am reducing it into 200 mm.